In this video, we'll start by proving a corollary of Gauss's lemma. This is corollary 6 in section 9.3. The setup is we'll let R be a UFD, F be its field of fractions, and P of X be a polynomial in R bracket X. And we're going to suppose that the GCD of the coefficients of P of X is 1. All right. The statement is that P of X is irreducible in R bracket X if and only if P of X is irreducible in F bracket X. So in particular, what's a common situation where you have a polynomial where the GCD of the coefficients is 1 is when that polynomial is monic, when its leading coefficient is actually 1. That means that the GCD of all of the coefficients will automatically be 1. So if you have a monic polynomial in R bracket X, it's irreducible in R bracket X if and only if it's irreducible in F bracket X. All right, so first, why is this condition on the GCD of the coefficients there? Well, let's just think about an example like P of X equals 7 times X. This has coefficients in Z bracket X. You can think of it as an element in Q bracket X, and it's irreducible. Why is it irreducible? 7 is a unit in Q bracket X, and X is irreducible. Right? So it's a unit times an irreducible element. But in Z bracket X, you can write it as 7 times X. And these are both non-zero, non-unit elements in Z bracket X. 7 is a non-unit element in Z. The difference is that 7 is a unit in Q, but it's not a unit in Z. So this polynomial is reducible in Z bracket X, but it's irreducible in Q bracket X. So this condition of having the GCD of the coefficients being 1 makes sure that this doesn't happen. All right, so let's prove this statement. And Gauss's lemma gives us one direction. We've already seen that reducible in F bracket X implies reducible in R bracket X. So what we're actually going to prove is that P of X is reducible in R bracket X if and only if it's reducible in F bracket X. But you can see why these two statements are equivalent, because you're either reducible or irreducible and not both. So let's suppose that we have a factorization of P of X in R bracket X that shows that P of X is reducible. So P of X equals A of X times B of X, where A of X and B of X are non-zero non-units in R bracket X. Well, now the problem would be maybe you have this factorization of non-zero non-units in R bracket X. Certainly, these are two elements in F bracket X. But what if one of them became a unit? Then you would be in this situation here. So if one of them became a unit, then that wouldn't be enough to show that P of X was reducible in F bracket X. So what are the units in F bracket X? They're just the degree 0 polynomials that are not 0. They're the units in F. So we just have to show that both of these have positive degree. So since the GCD of the coefficients of P of X is 1, the degree of A of X and the degree of B of X have to be at least 1. Why is that? Because if A of X had degree 0, it's not a unit. So that would mean there's some irreducible factor in this degree 0 polynomial. And all of the coefficients of P of X would be divisible by that irreducible factor. So because of this GCD condition on the coefficients, we know that doesn't happen. So A of X and B of X have degree at least 1, which means they don't become units when considered as elements in F bracket X. So now this is a factorization in F bracket X that shows that P of X is reducible in F bracket X, because it's a product of two non-zero non-units in F bracket X. So the same factorization shows that P of X is reducible in F bracket X, and that's the end of the proof. So what are we seeing? We're seeing that this condition on the GCD of the coefficients of P of X is 1 plays an important role. We have to rule out this kind of example. And then in the proof, we actually use this GCD condition to say that these elements that are non-zero non-units in R bracket X don't become units in F bracket X. So I'm going to pause and erase, and I'm going to prove something that's often paired with Gauss's lemma in many other sources. It's not explicitly stated in this way in Dummett and Foote, so it's something I think you should be aware of that will help you to go to look up other sources and other references for this material. let f of x be equal to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. We'll define the content of f of x to be the GCD of its coefficients. So where are we? Let's just talk about this concept when we're in a polynomial ring R bracket x where R is a UFD. So in a UFD, we can talk about GCDs. And this GCD of a bunch of elements in our ring R, this is well defined up to a unit in R. So so the GCD, remember we talk about a GCD rather than the GCD. It's only well defined up to a unit. And okay, so the main thing that I want to talk about in the rest of this video is how does content behave under a product of two elements in R bracket x. So first, if the content of capital F of x is the same as the content of capital G of x is 1, if these are for two polynomials, f of x, g of x in R bracket x, that is, we have two polynomials and each one has the GCD of its coefficients equal to 1. There's no irreducible dividing all of the coefficients of f, and there's no irreducible dividing all of the coefficients of g. Then the same thing is true of the product. The content of the product, f of x times g of x, is also equal to 1. More generally, if you have little f of x, little g of x in R bracket x, the content of the product is the product of the contents. So the first special case actually is the important one to remember how it goes, and then we'll see how to use the special case to prove the more general fact. Let's argue by contradiction to prove the first statement. So we'll suppose that there is some irreducible element p in the ring R that divides all of the coefficients of f of x times g of x. That is, we'll suppose that the content of the product is not 1, that it has some irreducible factor. There's some irreducible factor of all the coefficients. So this GCD of all the coefficients is not 1, that it has some irreducible factor. OK, so p is irreducible in a UFD, which means that it's prime. And we've already talked quite a bit about this ring homomorphism that you apply to R bracket x, where you reduce all of the coefficients of your polynomial modulo the ideal generated by p. So what happens is we apply this homomorphism, and if p divides all the coefficients in the product, then when we reduce all of the coefficients modulo p, we just get 0. So the image under this reduction, the image of capital F and times the image of capital G, is 0 in R modulo the ideal generated by p bracket x. And what do we know about this ring? This is an integral domain because the ideal generated by p is a prime ideal. OK, so what does that mean? That means that either the image of capital F or the image of capital G is 0 in this ring. And what does that mean? That means either p divides all of the coefficients of f or p divides all of the coefficients of g. This is just like what we saw in the proof of Gauss's lemma. And either way, this contradicts the assumption that both f and g have content 1. It's not possible for there to be an irreducible element p that divides all the coefficients of f or that divides all the coefficients of g. All right, so I'll pause and erase. And the last thing that I'll do in this video is show you how to use this first statement to prove the second statement. Let's prove this second statement about content being multiplicative. All right. So we have some polynomial, little f of x, and the content is something. The GCD of the coefficients is something. Let's say that it's d. Well, that means that we can pull out a factor of d from all of the coefficients. D divides each one of the coefficients, and write little f of x as d times capital F of x, where the content of capital F of x is 1, that the GCD of the coefficients of capital F is 1. And similarly, we can write little g of x as d prime times capital G of x, where the content of capital G is 1, and d prime is the content of little g. Okay, now let's look at what happens. Little f times little g, this is the thing whose content we're trying to understand. That is equal to d times d prime times this capital F times capital G. And now we take the content of the polynomial on the left-hand side. That is d times d prime times the content of this polynomial, capital F times capital G, because how do you multiply a scalar by a polynomial? You just multiply every coefficient of that polynomial by that element in your ring. So d times d prime divides every coefficient of this polynomial on the right-hand side. So we see as the content of little f times little g is d prime times the content of capital F times capital G. But by part 1, capital F and capital G are two polynomials where the GCD of their coefficients is 1. So the same is true for the GCD of the coefficients of the product, the content of the product. So the content of little f times little g is d prime, and that is the content of little f times the content of little g. Okay, so I wanted to talk about content because very often, if you go to sources other than Dummett and Foote and you read about the proof that when R is a UFD, R bracket X is also UFD, you'll see this result about content being multiplicative and Gauss's lemma together used to prove the main theorem. So we could have proven this lemma first and actually used it a little bit during our proof of Gauss's lemma, but not really in a significant way. So there's one statement in the proof that's given in Dummett and Foote where I really do want to use this result, and we'll see that in the next and final video of this lecture.